Dear students, in this class we will learn or we will discuss about differentiation of a function, and uh, and then we will apply the process, the method or technique of differentiation of some functions, that is to solve some problem. Now come to the point differentiation. Here is that differentiation. If you have given a function y that is equal to fx, that is, in this case, y is the dependent variable and x is the independent variable, and then the differentiation of this y with respect to x is given by or denoted by dy by dx, and the process of finding the rate of change of variation of the dependent variable with respect to the independent variable is actually called the differentiation. That is, here is the dependent variable is y and the independent variable is x. Then if dy is the change of y when x changes to dx, then the rate of change of the dependent variable with respect to the independent variable is dy by dx, and this is the differentiation of y with respect to x. Now come to an important point, that is derivative at a point. So if fx is a function defined for all real values of x, then so if you have a given function fx and that fx is defined for all values of x, then limit h tends to 0 fx plus h minus fx by h if this quantity exists and finite. So now you have given a function and you have to just calculate the value of limit h tends to 0 fx plus h minus fx by h, and if you find that this value is finite and exists, then you can write dy by dx, that is equal to the differentiation of the function fx, that means f prime x, that is equal to limit h tends to 0 fx plus h minus fx by h. That is, this term is actually the differentiation of y with respect to x, and this is actually then called the derivative or the differential coefficient of fx. So to calculate the derivative of a function, we can first find out the value of fx plus h, and then calculate this limit, that is limit h tends to 0 fx plus h minus fx by h, and if it exits and has some finite value, then the differentiation of y, that is equal to fx with respect to x, is given by or the definition of the differentiation of y with respect to x is given by this formula, that is f prime x is equal to limit h tends to 0 fx plus h minus fx by h, and we can use this relation or use this expression. Now, however, if the point is taken, that is the differentiation at the point x is equal to a, can also be written as a prime a. In this case, x is equal to a, that is equal to limit h tends to 0, and then function of a plus h minus a plus h minus fa by h, because in this case only just the point is taken as a. So from this relation you can comfortably write a prime a is equal to h tends to 0 fa plus h minus fa by h. So this is the differentiation of the function f x, function of x with respect to x at the point x equal to a. Obviously, in this case, the condition that should be followed or that should be obeyed is that this limit should exist. That means, in that case, the left hand limit and the right hand limit should have finite values, and they are equal. So now some standard derivatives. So one, just in this case, in this section, you have to remember that the differentiation of a function, that is fx with respect to x, can be calculated by using this relation. Okay, now come to some standard derivatives. You know all about this in your previous class, that is in HS standard class, and these are some standard derivatives are given here, and you need to go through this and you need to apply these derivatives when you require. Okay, so when they require. Now here are some standard derivatives, and here are also some standard derivatives, and after that you should note this type of relations, and this type of relations very often or very frequently can be required in case to find out the derivatives of a function with respect to another function. That is where cos hyperbolic x is equal to 3 over x plus e to the minus x by 2, and sin hyperbolic can be written in this session, and similarly cos hyperbolic inverse x, sin hyperbolic inverse x, tan hyperbolic inverse x, and these are the forms, and this form can be used when they required. And here are some theorems on derivatives, and you know this kind of theorems, that is dx of fx plus minus gx, that is d fx dx plus minus dgx by dx, and you know when for the derivative of multiplication of two functions, then one function is to be kept constant, and the derivative of another function should be carried out, and then and vice versa, and just sum of them, add them. So this can be written as this in this fashion. And similar and another theorem is there, that is ddx of fx by gx, and if the functions are in the form of fraction, then you can write the derivative will be first keep these gx as constant, then just differentiate these fx, that is here, and after that keep these fx constant, that is here, and differentiate this gx, that is here, by this gx whole square. So this has the form, if it has the form d dx of uv, then write v du dx, then u dv dx by v square. Okay, and if you have given a function y is equal to fu, and further u is equal to fx, then dy by dx, that is dy by dx, can be written as dy by du and into du by dx. So you can write in this fashion, and a similar way, if you have a given function y is equal to fu, then fu is a function of v, sorry, u is a function of v, and further b is a function of x, then you can write dy by dx is equal to dy by du, then du by dv, then dv by dx in this way. So this is called the chain rule. Now difference derivative of a function with respect to another function. So let us consider that you have given a function y is equal to fx, and another function z is equal to function of g function of x. Then you have to find out the value of dy by dz. So dy by dz can be written dy by dx and then by dz by dx. You can write this as in this form. So that is equal to, you know that dy by dx, that is equal to ddx of fx, that is z prime x, and dz by dx, that is equal to ddx of gx, that is g prime x. So dy by dx can then be written as z prime x by g prime x if they are the function of x, that is they can be represented by this. Okay, now derivative of a parametric function. If x and y are functions of a variable or parameter t such that x is equal to ft and y is equal to gt, then you can write dy by dx is equal to dy by dt by dx by dt, that is equal to g prime t by a prime t. You can write this in this way. Now another important point, that is derivative of implicit function. And you know that we are very familiar with equation in which y is expressed in terms of x. So you can, and we see, and we very often have seen relations expressing y and x in the left hand side y and the right hand side x. So in that case, y is said to be explicit function of x. That means in that relation, the left hand side is only contents of y, and the right hand side contains only the terms related to x. So in that case, there is no mismatching, mixing of. In that case, there is no mixing of y and x variables. So in that case, y is said to be an explicit function of x. However, in some relation, in some cases, and there it is observed that both the terms on the left hand side and the right hand side expressing the relation with x and y contains both terms contain both terms. So it is a relation that x square minus y plus xy, that is equal to x cube plus 3y plus 9. So in this relation, the left hand side and both the right hand side contains both terms, both variable x y y, x and y. In that case, this kind of relations, in that case, this kind of perform this kind of relation, you can write fxy is equal to 0. That means if you bring the right hand side to the left hand side, then the right hand side will be actually 0, and left hand side can be written in this form fxy. And in that case, then y is said to be an implicit function of x. Okay, and in that case, if you differentiate this y with respect to x, so in that case, by differentiating each term, so here there are two terms are there, and then just differentiate both terms with respect to x. In that case, keeping y is a function of x, obviously, and then collecting the terms of dy by dx, you can find out the required result. Okay, and the example of this kind of, that is implicit function of x, will be given in this class, will be solved in this class. So we come to know, or we learn from this topic that if y is a function of x, it can be two types. One is ex, explicit function of x, y as explicit function of x, and y is implicit function of x. If y is completely a function of x, that is in the relation describing the equality of y and x, in that case, and the right hand side, if y is written in the left hand side, and its relation with x is written in the right hand side, then if the right hand side only contains the terms related to or associated with x, then y is said to be uh, an explicit function of x. If, however, both the left hand side and the right hand side contains both x and y, that is the dependent and independent variables both, that is it is mixing of both variables, then furthermore, if y is a function of x, then in that case, y is said to be an implicit function of x. And in case of implicit function of x, you can write the relation between x and y in this fashion, that is fxy is equal to 0. And then just to differentiate this expression, that is both term containing x and y with respect to x, keeping y or considering y as a function of x, then collect the coefficients or collect the values of dy by dx, and in this way you can find out the derivative of y with respect to x. So that will be done in some examples. So first example is, if f(x) is equal to x square plus 2x by x square plus 5x, find dy by dx. So it has the form, and the function has the form u by v, and you know that and also you can, so if it has written here y is equal to fx, that is equal to x square minus 2x, x is equal to 5x, and he has the form, I already said that it has the form u by v, and you know that the formula is written here. The formula is written here, that is v is taken first constant, then du by dx, then u is taken as constant, du by dx by v square. So here u is x square minus 2x, and v is x square plus 5x. So then you can write dy by dx is equal to ddx of this, that is first here x square plus 2x, 5x is constant, then ddx of x square minus 2x. After that, you should keep x square minus 2x as constant and derivate and differentiate this. So that is done here by x square plus 5x whole square. and this is the simplification. And after simplification, you finally get dy by dx is equal to 7x square by x square plus 5 whole square. This is the required value of the differentiation of y with respect to x. So another problem is here. Just you need to go through these steps, and you have to calculate yourself, and then compare with these calculations. Okay. Now find dy by dx when x is equal to a into t plus sine t and y is equal to a cos t. So here you have to calculate the value of dy by dx. Sorry, dy by dt. Since in this case y. So to do this, see here there are two functions. One is x, which is a function of t, and y, which is also a function of t. So in this case, if you have to find out the value of dy by dx, so first you have to calculate dy by dt and then dx by dt. After that, you can comfortably find out the value of dy by dx using this formula dy by dt by dx by dt. So here y is equal to a cos t, so and x is equal to a into t sin t. So dy by dt from here minus a sin t, and from here dx by dt is equal to a into 1 plus cos t. Okay, now just substitute the values of dy by dt and dx by dt in this relation. That is, it will be the numerator is a sin t and the denominator is a into 1 plus cos t. Now just write the sine t can be written as sine of 2t 2 into t by 2. So that can be written as 2 sine t by 2 cos t by 2, and 1 plus cos t can be written as 2 cos square t by 2. So just simplify with a negative sign. This negative sign arises from this term. So finally dy by dx is minus tan t by 2. Another example is here. Find derivative of cos inverse 3 cos x minus 2 sin x by root 13 with respect to sin inverse this. So here are also two functions. Let y is equal to this, that is cos inverse this 3 cos x minus 2 sin x by root 13, and z is equal to this term, that is sin inverse 5 sin x plus 4 cos x by root 41. And now just consider or take another substitution, that is 3 is equal to a cos theta and this 2 is equal to a sin theta. Then you can write from these two tan theta is equal to a sin theta by a cos theta. So that is equal to a sin theta is equal to 2 and a cos theta is equal to 3, that is theta is equal to tan inverse 2 by 3, and square and add these two terms, so that is 3 square plus 2 square is equal to a square cos theta sin square. That means that is equal to 13, or from here a is equal to root 13. So from here, that is from this relation, you can write y is equal to cos inverse a. This from you understand that here a term a will arise here, and from here another a is the arise from, so that a is here. So that is cos inverse a. Then this 3 is here, a cos theta is taken here, so cos theta and then cos x minus here sin x, then sin theta by a. Just substitute the value of these 3 and these 2 here by a, because you know that root 13 is equal to calculated as root 13 calculated as a. So this a is written here. So after that is y is equal to cos inverse cos x plus theta. That means cos inverse cos x means x. So that is y is equal to x plus theta, and from here dy by dx is calculated here 1, or you can calculate dy by theta, that is equal to 1. So now you can similarly substitute 5 as p cos theta. P is another constant, and 4 is equal to p sin theta. And from here tan theta is equal to 4 by 5, that means theta is equal to tan inverse 4 by 5, and p square into sin square theta plus cos square theta, that is squaring these two terms and adding them, you can obtain that this term is equal to 5 square plus 4 square, or from here p is equal to root 41. And now it is time to substitute, it is the time to substitute the values of these 5 and 4, and also this p in this expression, that is forward, or in which expression, that is the expression of z, that is in this expression. So that is done here, carried out here. Sin inverse then p sin x plus theta by p sorry, here sin inverse p sin x cos theta plus p cos x sin theta by p. Just substitute the values of 5 and 4 in this expression. So you can simply obtain this. So sin inverse of this, that is x plus theta finally, or from here dz by dx, that is equal to 1, or dz by theta, that is also 1. So dy by dz, we can calculate, write it as dy by dx by dz by dx. That is equal to 1 by 1. That is equal to 1. You can also prove it by using the relation dy by dz is equal to dy by d theta, then dz by d theta. Okay. And in that case also, since dz by theta is equal to 1, and and also dy by d theta is also 1, that is calculated here, that was calculated here. So in that case also dy by dx is equal to 1. So dy by dz is equal to 1. So this is the value. So the differentiation of the first term with respect to the second term, that is the differentiation of these with respect to this is essentially 1. Now another problem is here, root over y plus x plus root over. See, one thing. Okay, first write this problem: root over y plus x plus root over y minus x. That is equal to c. So in this expression c, the left hand side actually contains both terms, that is y and x, and this term is equal to c, that is fx y, that is equal to c. So this is a relation, and in this relation you can say that y is an implicit function of x from the definition that we have discussed earlier. So this kind of relation is an example of implicit function of y, and in this case y is a function of x, and in this case y is said to be an implicit function of x. Okay, no problem. Now we have to solve this, and in this case we have to show that dy by dx is equal to dy by x minus root over y by x whole square minus 1. And here c is a constant, it is stated here. Now the given function is here, that is root over y plus x plus root over y minus x is equal to c, and you can write this as y plus x to the power half plus y minus x to the power, that is equal to constant. Now differentiate this equation, and in this case you know that if you desire to find out the value of dy by dx, so you have to differentiate this expression with respect to x, okay, with respect to x, keeping y is a function of x, and after that collecting the values of coefficient of dy by dx, you can calculate the desired value of dy by dx. Okay, so no problem. So first differentiate both sides of this equation. So that is here with respect to x. So that will give you, first half is here, then y plus x to the power half minus 1. That means the half to the power minus half. Then you have to differentiate this term within the parenthesis, that is within the bracket. So first term is dy by dx. Since y is a function of x, you have to use this concept, and then plus 1 from here. That is after that plus half, then y minus x to the minus half, and then this term will provide you dy by dx minus 1, that is equal to 0. And you can write this term is equal to this term with a minus, and that is done here. Then half will cancel. So from here dy by dx, so just bring this term related to dy by dx to the left hand side and the rest part to the right hand side, rest terms. So from here dy by dx is here, okay, and this term is multiplied with this, so this term is essentially root over y plus x. So dy by dx, just multiply this, first multiply this with this term. So first dy by dx into 1 by root over y plus x, then plus 1 by root over x. In this way the right hand side is here. So now bring this term to the left hand side, so dy by dx, then y 1 by root over y plus x, then this term is here with a plus sign, that is equal to this term 1 by root over y minus x, and this term, this term is taken here with a negative sign. So just simplify now, dy by dx, that is equal to y minus x plus y plus x by root of y plus x root y minus x, you can write it, and the right hand side is here this. So this term will cancel each other. So dy by dx is equal to root y plus x minus root y minus x by root y plus x plus root y minus x, and that can be written in this fashion, in this way. That is, multiply both the numerator and the denominator by the term by the term y plus x minus root over y minus x. That is done here. So the numerator now is y plus x minus y minus x whole square, and the denominator is root over y plus x whole square minus y minus x whole square. So just calculate the numerator now will provide you y plus x from the first term. Then this square will give you y minus x, then minus 2 root over y plus x root over y minus x by this square plus this square. That means y plus x, then minus y plus x. So that is equal to 2y minus 2 root over y square minus x square by 2x. These two, and these two will cancel, and finally you get here from here dy by dx is equal to y minus root over y square minus x square by x, and just simplify this. This can be written as y by x minus root over y square by x square minus 1, because from here x square is taken outside the square root. That means they are then this x will turn into x, and then it will be y by x minus root over y square by x square minus 1, and here x and in these x will cancel each other. So finally dy by dx is equal to y by x minus y square minus 1 root over y square by x square minus 1. This has been proved. Now another function is y is equal to function of 2x minus 1 by x square plus 1, and you have given that f prime x is equal to sine x square, then find dy by dx. So just let u is equal to this term, that is 2x minus 1 by x square plus 1. So you can write from here y is equal to f of u, function of u. And so if you wish to calculate the value of dy by dx, so you can write dy by du into du by dx. That is from the chain relation, and that is equal to you know that this dy by du, as already you know that y is equal to fu, so dy by du is equal to f prime u, and then du by dx. And also it is given here that f prime x, that is equal to sine x square. So f prime u, just replace x by u, that is equal to sine u square, because since f prime x is equal to sine x square, so sine u square, that is equal to sine, just use the value of u. You have taken the value of u as 2x minus 1 by x square plus 1. So that is sine 2x minus 1 by x square plus 1 whole square. Now you have just here to calculate du by dx, because you already find out the value of, because dy by dx is finally has the form f prime u by du by du, and in this case you have already calculated the value of f prime u, that is here this. So now we have to calculate du by dx. So du by dx is here, ddx of 2x minus 1 by x square minus 1. So you know the formula, required formula. First you have to keep this as constant and differentiate this, that is here, and after that keep 2x minus 1 as constant and differentiate this term, that is here, by this term square, that is here. So this is the simplification process, and just go through this, and after that you obtain that this du by dx is equal to 2 plus 2x minus 2x square by x square plus 1 whole square. Just go through these lines, every steps are carried out here. So dy by dx is equal to f prime mu du by dx, and so this was the relation that was found here, that was found out here. So now f prime u, you have already known, the value of f prime u, that is here sine 2x minus 1 by x square plus 1 whole square, that is here, and then the value of du by dx, that is this value, that is here, and multiplied with this. This is the required value of dy by dx. Now another example is here y is equal to x to the power x to the power x to the power x, in this way up to infinity. Then you have to find dy by dx. So here the given relation is y is equal to this, and this can be written as y is equal to x to the power y, because just think of these terms except the first one. So first one is x, okay, I have written here, and then the power of x is x to the power x to the power x to the power this is in this way. So except this term, the rest terms are infinity minus 1. So total infinity, so these terms are infinity minus 1, okay. So you know that if 1 is subtracted from infinity, actually that will provide you infinity, that the large number, the huge number. So in that case you can also write x except the first x to the power x to the power in this way to a infinity minus 1, that is nothing but y. So you can write from here that y is equal to x to the power y. Now taking logarithm, natural logarithm, that is the base with the base e on both sides, that will give you log y, that is equal to log x to the power y, that is y log x. Now differentiating both sides with respect to x, first this will give you 1 by y dy by dx, and then from here y is constant, then log x will y to 1 by x. After that log x is constant, and then y is dy by dx. So here also, see here, this is also in this case also y is an implicit function of x. So in this case, we have to collect the coefficient of dy by dx, the values of dy by dx. That is here. So 1 by y dy by dx. Then from here minus log ex dy by dx, that is equal to y by x. From here dy by dx into 1 by y minus log ex, that is equal to y by x. Or from here we will calculate it, that dy by dx is equal to y square by x into 1 minus y log ex. So this is the simplification steps. Just go through this. So in this case, we finally we able to find out the value of dy by dx. So this is the way through which we can find out the value of dy by dx, in which case y is an implicit function of x. So now come to another important topic, that is differentiability of a function. So it is very important, because before going to differentiate a function, so you need to know whether this function is differentiable or not. So let you have given a function fx, and this fx is said to be differentiable for a certain point, that is for a certain value of x, that is equal to x0, if both the left hand derivative and the right hand derivative of this function exist finite and equal. So what are the left hand derivative and the right hand derivative? I will discuss it here. So don't worry with this. So the condition, required condition, essential or necessary condition of a function to be differentiable is that the left hand, so for us obviously they are the for a certain point, that is x equal to x0, the left hand limit and the left hand derivative and the right hand derivative should exist, and they have finite values, and they should also be equal. So now I am here expressing the left hand, denoting the left hand limit as left hand derivative as l a prime x0, that is at the point x0, and the right hand derivative by r a prime x. And these are, I am denoting these, or the left hand derivative or the right hand derivative are denoted by l a prime x0 and r a prime 0 respectively. And the definition of left hand derivative and the right hand derivative are also written here. The left hand derivative at the point x 0, at x is equal to x0, is given as limit h tends to 0, then function of x0 minus h minus f x0 by minus h. This is the definition of the left hand derivative. And in the similar way, the definition of the right hand derivative at the point x is equal to 0, x is equal to x0, sorry, is r a prime x0, that is equal to limit h tends to 0 if x0 plus h minus f x0 by h. So however, if left hand derivative and the right hand derivative exist, so you have given a function fx, and you have calculated for a certain value of x, that the left hand limit and the right hand limit both exist. But if however they are not equal to each other, they are not equal to each other, or they have not finite values, uh, then the function is said to be non-differentiable at the given point. Okay, and graphically it can be represented in such a way that if a given function is plotted on a graph and it has corner on it, that is on the graph. So here is an example. So it is the point x equal to x0. Here, see here, there is a corner of the graph. And if you draw tangent here, the nature of tangent, the value of tangent for this curve and for this curve are not equal. So in that case, the function should not be differentiable with respect to x at the point x equal to x0. And similarly, another example is here. This is the plotting of y is equal to mod x. Okay, and in this case, at the point this x equal to x0, that is, it is nothing but the origin. That it has a corner or break here, and in this case also, the y is equal to fx is not differentiable at 0, that is at x0 equal to 0. So these are the examples. So the necessary and essential condition or required condition of a function to be differentiable is that the left hand limit and the right hand limit both should exist, have finite values, and are equal. If it is not, or any one of them is not have is not does not exist, any one of them does not exist or has finite values, then the function will not be differentiable at the given point. Now here are some examples from which the above conception will be very clear. The first one is show that the function fx is equal to x square into sine 1 by x when x is not equal to 0 and fx is equal to 0. When that is x square into sine 1 by x when x is not equal to 0. And this function has value 0 when x is equal to 0. And you have to show that this function is continuous and differentiable at x equal to 0. So first we have to prove whether this function is continuous or not at the point x equal to 0. And to do this, we know that we have to prove that the left hand limit, that is, should be equal to the right hand limit. Obviously they should exist finite and equal. So that is done here. The left hand limit is here, limit x tends to 0 minus, that is equal to you can write this as limit f of 0 minus h by 0 minus h when h tends to 0. Here x is equal to 0 minus is the substitution is this. That is from here limit h tends to 0. 0 minus, because in this case x is here, x tends to 0 but less than 0. So that in that condition fx is this, because if x is not equal to 0. So x square sine 1 by x. So here is that x square means 0 minus h whole square, then 1 by sine 0 minus h. That is from here x square into minus 1 by sine h, that is equal to 0 into because you have this value has a finite quantity and this quantity is multiplied by 0, so it will result that this will result to 0. And now the right hand limit is here, h tends to 0, x tends to 0 plus limit fx, so that can be written as limit h tends to 0 f of 0 plus h. And in this case also, since x is not equal to 0, so you have to adopt the value of fx as fx of x square into sine 1 by x. That is also here done here. And and this is also done here, that is also done here, where that is here. So limit h tends to 0, 0 plus f of 0 plus h. So that is also calculated here, and in this case 0 into this is also finite quantity, so that is equal to 0. So also f0, that is also given, that 0 in the condition that f0 is equal to 0, it is also given. See here fx0 when x 0, that means f0 is equal to 0. So we understand, or we see from here that left hand limit that is equal to right hand limit that is equal to f0. So the given function is continuous at x equal to 0. Now the second part, that is you have to show that the given function is differentiable at x equal to 0, and if so, then the left hand derivative, that is lfx prime, is equal to right hand derivative, that is rx prime x. Now we have to calculate the value of left hand derivative, that is equal to limit h tends to 0 f of 0 minus h, because you know that from the definition that left hand derivative of fx, that is lf prime x, is equal to limit x tends to 0 h tends to 0, then function of x minus h, then minus f function of x by minus h. So here we just carried out since in this case h tends to 0, so that is also can be written as f of 0 minus h. Then since x equal to 0 point, at the point x equal to 0 we are calculating this, so 0 minus h, then minus function f of 0 by minus h. Now just you know that for x is not equal to 0, the function has the form x square sine 1 by x. So that is just using just substitute the value 0 minus x in this relation. That is, where is that relation? In this relation, if x is equal to x square sine 1 by x. And then this is and after calculation we finally obtain that this 0 into a finite value, that is equal to 0. Just it is similar to that of the previous one, so it is not very difficult to calculate. So now right hand derivative also can be calculated from the formula that limit h tends to 0, f 0 plus h minus f0 by h, that is here, that is here. So after that you calculated is that it is also 0. So left hand derivative and right hand derivative are equal, so the given function is differentiable at x equal to 0. Now another function is y is equal to fx, that is equal to x for x less than 1, and that is equal to 2 minus x for 1 less than is equal to 1 less than is equal to x less than is equal to 2. Show that another definition is there. This fx is also minus 2 plus 3x plus x square when x is greater than 2. Then show that it is not differentiable at the point x is equal to 1. So just the given function is here for x is equal to 1, that is x equal to 1, this condition is here. Then if x is equal to 2 minus x, then find the value of f1. So that is at x equal to 1, f1 that is equal to this 2 minus x, that is equal to, in this case 2 minus x is 1, so 1. So f1 is equal to 1. Now the left hand derivative of the given function is at the point x is equal to 1 is Lf prime x, that is equal to limit h tends to 0 function of, since the point is equal to 1, so here x should be replaced by x minus 1, that is 1 minus x, h, x minus h, that means 1 minus h, minus f of x, that means f of 1, then minus h here. So limit h tends to 0. Just see here in this case, since in this case since your x is, because in this case x is less than 1, so you have to, sorry, in this case since h tends to 0, and see also for the point x equal to 1 you are calculating this. So when x equal to 1, if x is 2 minus x, so this relation is taken here. So this from here you will have no, it is not. When is from the first relation, in this case that since it is the left hand derivative, so in this case x is less than 1. So in this case you have to use fx is equal to x. So here is it is done. X means first from here 1 minus h, then minus 1 by minus h, because it is the condition fx is equal to x for x less than 1, and you know that this f1 is equal to 1. So from here it is calculated as 1. Now the right hand derivative is if rf prime x, that is the limit h tends to 0, 1 plus h, because something is adding with h, minus f1 by h, and in that case the value of x is higher than 1, so you have to use the value of fx as this 2 minus x. So that is done here, 2 minus 1 plus h, then minus 1, since if x is equal to 2 minus x and 1 less than equal to x less than equal to 2 from this condition, and if 1 is equal to 1, and from here you finally find out that right hand derivative is minus 1. So since in this case left hand derivative and right hand derivative are not equal, so the function is not differentiable at x equal to 1, at x equal to 1. We have given another example. Show that the function fx is equal to x e to the power 1 by x by 1 plus e to the power x when x is not equal to 0, and 0 when x equal to 0. And this function is not differentiable at x equal to 0. You have to prove it. So see from the relation that when x is equal to 0, this fx is equal to 0. That means f0 is equal to 0. And now the left hand derivative, that is the left hand derivative is L f prime f, that is the limit h tends to 0, then in that case f of 0 minus h, then minus f of 0 by minus h. And you know that f0 is equal to 1 from that is sorry 0, that is calculated here or given here. So then limit h tends to 0, just use the value when x is not equal to 0, because in this case the value of x is just lower than 1 because h is lower than 0, so it is not equal to 0, so the first condition will be satisfied in this case. So we have to use the value f x equal to x e to the power x by 1 plus e to the power x, that is done here. X means 0 minus h e to the power 1 by 0 minus h by 1 plus e to the power 1 by 0 minus h minus f0 is equal to 0 since, and into 1 by minus h. This h is here. So just calculate, just use calculate, and finally you obtained, and the left hand derivative is equal to 0. And from now the right hand derivative, so right hand derivative also calculated here. The definition is h tends to 0 f 0 plus h minus f0 by h. In this case also x is not equal to 0, so the first definition of fx, that is this value should be used in this case. And after that, and also if this f0 is 0 also given there, so finally you obtain that r f prime, that is the right hand f prime x, that is the right hand derivative is also 0. So both the left hand limit and the right hand left hand derivative and the right hand derivative are equal, and they further also equal to the function or the value of the function at x equal to 0. So this function is differentiable at x equal to 0. Now another function is here, another problem is here. Find the derivative f x is equal to x minus 1 by 2x square minus 7x plus 5, x not equal to 0, and this is equal to minus 1/3 when x is equal to 1. At the point x equal to 1, you have to find out that this function is differentiable or find out the derivative of this function. So it is given here that at x equal to 1, so the function has the value f1, that is equal to minus 1/3. And now the left hand derivative is f l f prime 1. At the point 1 you are doing this, so that is equal to limit h tends to 0, and here x is 1, so 1 minus h function of, then minus the function of 1 by minus 1, and you know that the value of f, and you have to calculate this. Now to simplify this term here, this term x minus 1 by 2x square minus 7x plus 5, because in this case x is not equal to 1, so we have to use the value of fx is equal to this. So this is just simplified. After simplification you obtain fx equal to 1 by minus 2x. Just go through these steps. So now from this expression, left hand derivative is equal to h tends to 0, 1 by 2 into, since it here x is here, so 1 minus h minus 5, then minus f1, and f1 has the value minus 1/3, so that is plus 1/3, then minus h. Here is the calculation, just go through this, and you already find out that minus 2 by 9. So the left hand derivative is minus 2 by 9. So thus left hand limit, and since in this case you see here that the left hand limit and f1 are finite, both are finite. So the given function is differentiable, and the derivative of the given function is a prime x, that is left hand, because in this case you know that the left hand limit and the right hand limit becomes equal. So in this case you can check that the value of right hand, right hand derivative. So in this case the derivative, if you calculate, then you can check it, and you will able to find that the right hand derivative also will be this, and so the given function is differentiable, and the value of that is a left hand derivative, that is this minus 2 by 9. Okay, now this is the end of this class, and you need to go through all these calculations, and I think it will be clear to you.